All right, so welcome everybody. So first I would like to thank the organizers for inviting me here. It's a very nice place to be, a very nice workshop. So today I'm going to talk about neural networks and the most basic examples, which is like a single hidden layer. And the idea will be to try to see if we can make them provably tractable. Okay, so I'm not going to consider anything very deep, super like one hidden layer. And the main question is it possible to know in advance that I'm able to learn on some data, generalize correctly, and if possible have a polynomial time algorithm. Okay, so this is the goal of today. And because tractable is in the question mark, I will not achieve it. Okay, so big spoiler, there is still an open problem. Okay, the way I formulate it to probably show that you can, even for the simplest models, learn that hidden layer. So I'm going to consider the supervised learning problem. So we have seen that already several times. I want to attack it through the so-called curse of dimensionality. So here the idea is I'm going to learn some function f from Rd, and you should think of d as being quite large, and let's say hundreds, thousands, or millions. And I want to learn a linear function which is nonlinear, and I'm going to consider a loss L between my observations y and my predictions f of x, and the loss can be anything. Okay, so in that talk can be any Lipschitz continuous convex loss. Okay, it can be the SVM, logistic, or least squares. And so if you make the simplest assumptions, like f star is just assumed to be like Lipschitz continuous, then we have the classical curse of dimensionality. If you want to achieve the optimal test error, okay, so here R of f will always be the test error, expectations under my unseen data. So if I want to have an excess risk of epsilon, I need exponentially many observations and exponentially in dimension. Okay, the main reason is like a simple 2D plot. So the space of Lipschitz continuous function is very big, and it can be any like small bump, okay, located anywhere. So if I want to learn that small bump, I have to sample everywhere up to the point where I see that small bump. Okay, so this is like a zero-line proof of the curse of dimensionality. And the goal is to be robust to that. So clearly, there are lower bounds showing that you cannot do better. So what statisticians have designed in the last 50 years is a sequence of assumptions to make this possible. Okay, so we're going to make stronger assumptions on f star. So we're going to restrict the class of problems we're going to consider, and hopefully this will lower the sample complexity. So let's look at the list of models which have been used quite a bit. First, linear functions. Okay, clearly this is like more scalable, but this is really like a strong assumption. Then you can move from additive models to so-called generalized additive models when you take sum of functions of individual variables. This is something which is used quite a bit. Then you have the one-layer neural network, which I will come back to, with a fixed number of layers. Then you have projection pursuit, which is very similar, where you replace a fixed activation function by an unknown activation function which you learn on the fly, fi, and even more generally, subspace dependence. So you assume that your optimal predictor depends only on the subset, like a linear function of your inputs, and clearly you want here W to be rank efficient, otherwise kind of useless. So on the positive side, in this talk, it turns out that neural networks will be able to be totally adaptive to this. So for all of those, typically, you need a spatial algorithm to learn for that class of problems. Okay, so if I'm doing projection pursuits, there are a ton of algorithms, and same thing for that one, and same thing for all of them. It turns out that neural networks can indeed achieve a good sample complexity. Okay, so what I mean by having a small number of a small n to learn by just changing a single parameter, and what we will achieve will be something like this, where okay, for linear functions we get like 1 over epsilon square, for a generalizative model 1 over epsilon 4, and the dependency dimension is only polynomial. For neural networks we get just like something so epsilon square, but 1 over epsilon square. Projection pursuit also 1 over epsilon 4, and if you depend on the subspace, it is exponential on the rank of W. Okay, so those results by themselves are not new. Okay, so for any particular submodel, those have been obtained before, but the key here is to show that with a single model, you can adapt to all of those. Okay, so this is the main goal of today, is to show that this can be achieved. Then how can this be achieved with a polynomial time algorithm is another story. I'm going to consider single layer neural networks, and one motivation of this work was to look at the so-called rectified linear units, because all my colleagues in deep learning, they say it's a great activation function. I want to see if it made any difference. It doesn't make much difference, but a little bit, as I will show. So this is mostly for notation purposes. I have my inputs X in RD. I have my hidden layers, and my hidden weights will be called W and B, and my output weight will be eta. And my hidden neurons will be, of course, like this rectified linear unit taken at an affine function of B. So in fact, most of the things I will talk about today extend to all homogeneous activation function. Okay, so what I'm going to use is only the fact that this function, the max, is only positively homogeneous. So everything essentially applies to all such functions. All right, so the questions I will try to answer in this talk are three kinds. The first one is, as I already mentioned, how do these generalize? So if I try to fit such a model, can I be adaptive to the structures which I've mentioned earlier on? And this will require both both estimating the estimation error and the approximation errors that I will make explicit in a moment. And another key question is, what if D is large and really large? Okay, so like exponentially large, like people do in compressed sensing. And we'll see that this can be tackled as well with that class of models. Then another aspect is, how do I get those weights? Okay, W here, so the hidden weights, W and B. And the core of the work is to let K go to infinity, so the number of neurons go to infinity and to reach a continuous limit. And then whether you put an L2 or L1 norm on the output weights will lead to different interpretations. Okay, so random sampling will be like L2 norm and eta, and learning will look like an L1 norm and eta, and the hope is to make this explicit in a moment. And finally, where things don't work, this is how can we get algorithm that run in polynomial time with guarantees. Okay, so if you run like a Bach propagation, it does run in polynomial time, okay, because you stop it at one point, but there are no guarantees. And the goal here is to have guarantees not on the training data, but guarantees on the unseen data. Okay, I really want to make sure that I predict correctly on unseen data. And again, this will not be achieved, but the goal is to identify what we need to be able to do this, and we'll see this in a moment. All right, so first this L1, L2, or sampling versus optimizing. So the first thing that people have tried a lot is to take those weights, those like inner weights, Wi, Bi, and to sample them randomly from a given distribution. And then if you now assume those Wi and Bi are fixed, this corresponds to linear predictions. I have features which are known. Those are those functions. I'm going to put some L2 regularizer, and this is known to be equivalent to using a kernel method. And since this is now 2017, people have forgotten about kernel methods. So let me give you a 2-minute review of kernel methods. So this is a problem dealing with linear predictions, some features phi of x with some penalty eta square. And the most classical theorem in that area, which is two-line proof by Kimelov and Waba, is to show that if you try to minimize the functions that depend only on function evaluations at your input data points, and which is increasing in eta, then the solutions has to be a linear combination of your input data points. Okay, it's just like Pythagoras theorem. And the beauty is that then you can take this, put it back into that, and you realize that everything will depend on the so-called kernel between two inputs, k of x prime, which is a dot product between phi of x and phi of x prime. So this leads to the traditional theory of log RK-HS, which is not the topic of today. But the key is that whenever you do learning with fixed features and linear predictions on those features, computing the kernel will tell you what you end up doing. Okay, so this is a two-minute review of kernel methods. So now let's go back to my case. So now I have to study that kernel. So excuse me for the overloading of K. Okay, so K is a kernel, is also the number of neurons. Sorry about that. Okay, so let's K go to infinity, and since I'm sampling W and B ID, then by the law of large numbers, it converges to the expectations under my distribution, so W and B, and then this is also a valid kernel, and hence, if you let the number of neurons go to infinity, you end up using kernels. Okay, so this has been known for quite a while, from Radford-Neal in the 90s, and a very nice follow-up work by Raimi and Recht in 2007, and with several extensions so far. Okay, so here in that context, you can compute this. You can compute this in closed form for some distributions. So if you take mu to be essentially uniform on the sphere for W, and B being I forgot what, but things to make it easy to compute. This you can compute. So essentially, if you want to learn with infinitely many weights, this can be done in polynomial time, to just build a kernel. So this may be inefficient because this may be quadratic in the number of observations, because you have to compute the full kernel matrix, but at least you can let K goes to infinity and be able to learn on those problems. Okay? I will come back to that thing later on, and this will learn smooth functions. All right, so this defines a Hilbert space, like all kernel methods, and one way to defining this Hilbert space is simply to follow this and replacing empirical mean by expectations. So I'm going to consider f of x, which is an expectation of all possible neurons with a certain activation, a certain output weights eta. And when I'm doing this sampling weight, is equivalent to having a L2 norm, a squared L2 norm on my output weight. Okay, so this is really rephrasing that earlier one. So this is when you do sampling, this is L2 penalization. Now if you do optimizing, okay, so again to replace this finite sum by an integral, where mu is a measure. It is a signed measure because it can take positive and negative values, and we're only going to assume it has a finite mass. Okay, and clearly, if that measure is a bunch of Diracs, we recover that exact expression. Okay, so this is also very classical. And so one way to say I'm going to learn some finite set of eta is to say I'm going to the measure space, to the set of all measures, and I try to impose a sparsity. This is what many authors have done in the past. So you're going to get this formulation in terms of all possible measures d mu, and you penalize the total variation of mu, and for simplicity, I've assumed that mu as a density with respect to a base measure d tau to make things simple. Essentially, I replace L2, which I had before, by L1, okay, and the idea that because you have some L1 term, you're going to, at the optimum, only get supported by not a finite number of neurons, but hopefully a small number of neurons, or a small manifold of neurons. Okay, so this has been done several times, and either from the statistical point of view or more from the approximation theory or for machine learning. At the end, the core idea is that when you let the number of neurons go to infinity, you get a convex problem because you want to learn over a space of measures where f is linearly parameterized, and your penalty is convex. All right, so let's look at properties of this function space. So I've defined a norm. Okay, so if I give me a function f, that can be written as an expectation of those neurons with the L1 norm. This defines the function space. So what do we know about that space? The first one, that it is dense in L2. So this is true for any non-polynomial activation function. So if I replace the positive part by any non-polynomial, then I guess this density result, which is very classical. One hidden layer neural network can approximate anything. Then, other property is that if you know that norm of f, and I will explain what properties that norm of f later. If that norm of f is finite, okay, then you can approximate any function, okay, with a finite norm, f1 norm, by a finite number of neurons, okay, with with error epsilon, and the number of neurons is essentially grows as 1 over epsilon square. And in fact, the proof is simply applying like Frank Wolf, and I will come back to that also when I talk about algorithms. Okay, so this is like classical results. So one thing I've worked on like 3 years ago is improving that scaling. Okay, so from 1 over epsilon square to something which is in fact optimal, but not quite different, because this is like d over d plus 3 is a bit smaller, but when d is large, it's not really smaller. So it is more, I think, interesting by the relationship with mathematical objects called zonotopes, and I will come back to that later also in the talk. And similar results are obtained by Mascar from a different point of view. Okay, so here, this is a classical approximation theory point of view. I have a function space. Okay, I want to approximate it by a finite number of elements, and the number of elements grows as 1 over epsilon square or something a bit less, but with something that depends on the norm. So clearly, when I'm going to the problem with that approach is that if you take my Lipschitz continuous functions, like very like non-smooth, they will not belong to the space. Okay, so this is one instance of the classical curse of dimensionality. Any good function, those function spaces are far too small to be useful in practice. So we begin to approximate functions by f's of growing norms. All right, in fact, this is what we're going to do now. Okay, so the goal is to see how you can generalize. So the classical algorithm would be to minimize the empirical risk. So I'm assuming I have some outputs xi, yi, which are id, okay, from a given distribution. And I'm going to minimize the empirical risk subject to constraints for either the norm with the L1 norm, gamma 1, or gamma 2 when I penalize my measure with the squared L2 norm. Okay, so this essentially requires to bound both the approximation error and the estimation error. So let's do that. So first, in terms of estimation error, which is essentially finding a uniform bound between my expectation R on unseen data and my empirical risk. And this is like using standard tools from statistics, and you can show that since you reduce to functions which are with a finite norm, you can show this goes down to 0 as n increases, that's 1 over root n, and it does increase as delta. Okay, if you get a bigger ball, then you get a larger bound. Okay, so it's very, very classical. Then you have the approximation error, which is whose goal is to characterize the difference between the best test error on my ball, my bounded set, minus the best test error overall. And because I've assumed that my functions are my space of functions are dense in L2, then this thing will go to 0 as delta goes to infinity. And the question is how fast? Okay, so they will go to 0 as delta goes to infinity as an inverse power, and the goal is to find the power. Okay, so again, there are two sets of norms. Gamma 2, where the weights are sampled, and you should think of it as a kernel method. So this can be really easily learned. And gamma 1 is trying to get to use this L1 norm. The one thing which is obvious is because I have used like L1 norms and L2 norms, one space is much bigger than the other. So F1, which corresponds to the L1 norm, is bigger because the two norms are gamma 2 dominates gamma 1. Okay, so this is like will be very important in the end, because in fact in all the subsequent slides I will go back and forth between gamma 1 and gamma 2. Okay, we'll use gamma 2. Since gamma 2 is a simple norm, RKHS, you can get a lot of insight from that, and I will get access to gamma 1 through gamma 2, and let's do it now. All right. So first, what are sufficient conditions to have this finite variation norm? So as I mentioned earlier, if you just assume Lipschitz continuity, you won't get a finite norm, and to get a finite norm, a simple way is to assume that you are sufficiently differentiable. Okay, so in dimension d, you need to assume that you're d over 2 plus 3/2 differentiable. So this is not tight. It can be made tight by looking at the parity of d, which I didn't want to do. But essentially, the number of derivatives has to grow with dimension. This is very classical. So this is something which is often forgotten by my colleagues, is that the curse of dimensionality is only there because we don't look at very smooth functions. Okay. All right, so now the goal is to apply it to a very wide set of Lipschitz continuous functions. So you need to find a G, okay, which is a finite norm, which is less than delta, and with an error which is as small as possible. And what I was able to show is a precise dependence on dimension. So here nothing surprising, okay? It scales as 1 over the dimension. It has to be, we have to suffer the curse of dimensionality. This is not possible to do otherwise. And the numbers, whether it's 2, 3, or d plus 1, that doesn't really matter. The important aspect is this is 1 over dimension. Okay, so if dimension is large, this will grow very quickly. All right, so the proof, and this is where the homogeneity comes in, and the proof works because our ReLU, or the positive part, is homogeneous. Hence, we can recast this as learning on the sphere, and since you have learning on the sphere, or the hypersphere, you get spherical harmonics. And so I spent like two weeks in Barcelona by myself, and I learned about spherical harmonics, and this is the result of those 2 weeks alone in Barcelona. This is very nice, and there's a very nice book on spherical harmonics, so if you want to learn about them, there are several ways which are harder or simpler, but look at the book I use, it's very good. All right, so, but the key here is this is for gamma 2. In fact, those results are obtained for gamma 2 because for those who know about kernel methods, it's known that if you work like with translation invariant kernels, it all depends on the Fourier transform of your kernel. It's the same thing. It's the same thing here. You replace the Fourier transform by the Legendre transform, and this is possible for gamma 2. Okay, but the problem with gamma 2 is what if your function depends only on a low dimensional subspace? Okay, so I've mentioned like some linear substructure earlier on in the talk. So let's say my function f only depends on the first variable. Okay, f of x is g of x1. The problem with the kernel space is that it's only based on smooth functions with all derivatives. So if you have a function which is if g of x is, or f of x is only a function of g of x1, then essentially the kernel method cannot really adapt to it. Okay, it will still compute all derivatives. Okay, some of them will be small, some of them will be 0, but at the end it will still require to have all these other derivatives to be to exist. With gamma 1 it's not the case because gamma 1 is based on an L1 norm. So if you reduce to a smaller dimensional subspace, it can adapt directly. So hence, whenever you assume f depend on the s dimensional projection, you can replace d by s for gamma 1, but you cannot for gamma 2. Okay, so this is one of the technical reasons why gamma 1 is adaptive, because of this L1 norm aspect. All right, so now I have those two terms, one that decays as n and grows with delta, one that grows with when delta goes to 0. Then I have to cancel those, like to balance those two terms, and this is what I've done now. Okay, so let's look at various assumptions for f. So here, this is I take various assumptions for f. This gives me a certain value of delta, and what I show here is the test error. Okay, so a bound on test error, okay, which is by the same algorithm, but just adapting the value of delta depending on n. So this is what I showed earlier in the first slide of the talk. When I have a linear function, I get this usual 1 over root n performance. So what I've shown, like in the first slide of the talk, was epsilon equal to that, and inverting that relationship between epsilon and n. Okay, but that is this 1 over root n, which is classical for that assumptions. If you make no assumption whatsoever, just assume like Lipschitz continuity, we get back the curse of dimensionality. Okay, so this goes down to 0, but very, very slowly. If you take projection pursuit type of problems, then you don't get the curse of dimensionality because D appears like not exponentially, and if you depend on the subspace, you get a similar behavior. Okay, so it is just showing that the same algorithm can adapt to everything. If you think of it, because neural networks have this linear structure, it should adapt, and it does adapt probably. Then if you start to put like penalizing the inner weights by L1 norms, so here we have two sets of weights, the input weights from input layer to hidden layer, okay, and the output weights from hidden layer to output layer. So when I mentioned like L1 versus L2, for the moment it was on the output layer, but now I'm going to select to do things on the input layer. So in the input layer, so since you're doing sum of eta I sigma, yeah. So if you put an L1 norm on this one, you're going to do variable selection, okay? And so the question is, if you put L1 norms, can you get high-dimensional behavior? So if you assume that your function f only depends on the q elements, okay, can you recover it? And what we should expect from like the theory of compressed sensing is that we should get the exact same thing as the column on the right. On the left, you replace d by q and you add the log d factor, and this is essentially what we obtain. So you replace square root of d by square root of the number of non-zero elements in your number of variables which you want to consider, and you add the log d factor. Okay, so this is nothing really surprising. It's just showing that this can do a nonlinear variable selection. Okay. All right, so this is all the good news about those neural networks. And before I go to the bad news, I will take a few questions, one question at least.
Yeah, so just one verification. So here, this is the sum of the two terms, the approximation and the
yeah, this is the sum of the two terms, and you take delta, which is delta being being this, you optimize so that the sum is as small as possible.
So they have the same rate.
Yeah, exactly. Any other questions on those properties? No? All right, so this was assuming that I could optimize the empirical risk subject to this L1 norm constraint. So now let's look how this can be done. Okay, so I have a convex functional G of f, which I will now assume to be smooth and convex. So I have a smooth loss, okay, like least squares, a logistic. It is convex, and I have a constraint set which is a ball, a bounded ball. So I can use like Frank-Wolf. So this has been like reinvented and renamed several times, and so the idea of Frank-Wolf is very simple. I start at a given point, okay, it is an iterative algorithm. So at ft, I look at the direction of the negative gradients, okay, so very much like gradient descent, but instead of making a small step, okay, I try to make the biggest possible step in my convex set, okay, so I move as far as possible in that direction, okay, and if I want to stay in my convex set, which is this, I get to that point, okay, so and then I make a small move between where I start and the extreme point, okay, so this is the Frank-Wolf algorithm. Then there are several ways, several variants, whether you choose a line search on that line, or you use a fixed step size, and so either like a decaying step size or a line search, but at the end you get this very nice convergence rate. Is that after t iteration, the value of my function minus the infimum of my on my ball is going to zero as 1 over t, and this essentially this can be used for a constructive proof of the approximation of a function by a finite number of neurons. Okay, this is a classical proof in many textbooks. The other good aspect is that because every time I take a convex combination of where I am and an extreme point, so if I start from an extreme point, I get a convex combination of extreme points, of t extreme points, which is nice. All right, so this is a general setup. So what does it do for my problem? So the L1 ball, since I have an L1 ball, the extreme points are the so-called one sparse vectors. So said like more formally, if I take my set, which is a set of combinations of those things, So this is a convex hull of all of those functions. Okay, so I have plus of minus. Okay, because I can have a positive or a negative weight. This is my neurons, and the delta is because I want. If I don't have delta, this is of norm 1 because I select a single neuron, and because I want to have like to be an extreme point of my ball of radius delta, I get the delta over there. Okay, so here essentially, if I want to apply Frank-Wolf, I need to be able to do this minimization problem, okay, which is essentially maximizing a L2 dot product between an element of my between here. Okay, I need to be able to optimize over all possible W in B such a dot product. Okay, so this is a non-convex problem by design, but not by design, but it happens to be a non-convex problem where I have to look over a set of dimension d plus 1 of a certain dot product, which is the current gradient of my loss times my features. So this is essentially like what boosting is doing. So now let's look how this works. So my goal is to be able to minimize this, and essentially since Frank-Wolf works by adding neurons one after the other, the key problem to be able to run this in polynomial time is it possible to add a neuron in polynomial time? So this is my functional, the error, my training error. Those are my current gradients of my loss for my r at a point. And now formally what I need to be able to do is maximize this, okay, with respect to W and B. And this was nicely laid out by Benjo, Leroux, and co-authors like quite a while ago. So to be very clear, if I can do this in polynomial time, I'm done, okay, because I can learn, I can minimize my training error up to any given precision, hence I'm done. Okay, so now let's look how this is possible. All right, so let's look, there will be a bit of math now, because essentially what will happen now is that I will reformulate it, okay, but at the end I'm going to run a bit into circles, because I will not be able to reach anything which is tractable. Okay, so this is, I've been very frustrated by that fact, and I'm happy to pass on the frustration to you. So if you can find a way to do it, I will be very happy, because this is something I've thought over for a few months, and yeah, so if you find a solution, I will be very happy. So let me describe what I've done so far. So first, I have a classical trick. I have removed the W in B, because I'm lazy, by reparameterizing V in D plus 1 and Z as X1. The goal is to maximize something like that. Okay. So now I can separate the set of GIs which are positive and the set of GIs which are negative, okay, by introducing a new T, which is just like a scale version. So this is using the fact that I have like a positive homogeneity, and I get something like that, the sum over the positive ones minus the sum over the negative ones. All right, I can use a bit of convex duality, okay, so in fact this is, before I do it, if I just take like without absolute value, this is a max of a convex function minus a convex function. So it's a difference of concave functions. I can use convex duality to get something which will be also difference of convex functions. So the way it works is I max, okay, and I have to take the max with respect to, if I take the max over there, I get the positive part, the max over AI in 0, 1. And if I take the mean over B in 0, 1, I get also the positive part. Okay, so max because I have plus over there, mean because I have a minus over there. Okay, this is very very simple. Then I can invert max and mean, and clearly I have to be careful because I have two max and one mean. And believe me, I can do something like that. Okay, I can invert. Yes, so I take the max. I take that max outside, max over A. Then I get max of V, mean of B. It's a concave convex problem. I can invert it. So I get max over A, mean over B, max over V. And now I can take the max over V. And what I get is something which starts to look good because I get the maximum over A of the minimum over B of linear combinations of vectors indexed by I, and also a linear combination of vectors of similar vectors. So here what I have is essentially, I have essentially reparameterizing this. It's a Hausdorff distance. Okay, so let me yes, a Hausdorff distance because I have max. Okay, so max mean. Okay, sorry. Yes, so this is a Hausdorff distance between those sets of vectors. Okay, when B is varying, and those set of vectors when A is varying. Okay, so it defines two sets, and so finding the Frank-Rule step, trying to get the new neuron, is equivalent to finding the Hausdorff distance between two sets, and those sets are linear combinations of my TIs. My TIs are my input data points. Okay, so xi, this is my input data. Zi is just adding 1, and Ti is just adding a scalar value. So overall, the task of adding a new neuron is computing a Hausdorff distance between two convex sets. Okay, so when I saw that, I thought, oh, it's over. Okay, because it's a very classical problem. I'm sure it's easy to compute the Hausdorff distance between two convex sets. Those convex sets even have a name. They are called zonotopes. Okay, so let's look at what a zonotope is. So a zonotop is a convex combination. Is a combination of vectors with weight between 0 and 1. So these are essentially affine projections of hypercubes. So if you start with 3 vectors in 3D, and this is a set of vectors which are sums of those vectors with weight between 0 and 1. So this is one zonotop. If I have more vectors, I get something which is like with more corners. And what you can show is that in D equals 2, all centrally symmetric convex sets are limits of zonotops. This is not true in dimension greater than 2. So this has a names, but the problem is that it's still hard to compute the Hausdorff distance between zonotopes. So here I've shown like two zonotops defined by two sets of vectors, and the goal is in high dimension is to find a way to find those two distances, which is a Hausdorff distance between those two sets. And this turns out to be difficult. I have not been able to find anything reasonable for that. So I've tried. Okay, so here I've looked at all possible tricks that I knew, and one is approximating by ellipsoids, because when you see that, they really look like ellipsoids. Didn't work very much. Okay, was not able to use that. Then I've tried like many convex relaxations. Okay, so SDP, ellipsoid, and I've tried a lot. So what I've conjectured, okay, and this is I'm almost sure it's true, is that it's not possible in general. So if I give you a bunch of G's, so the G's are those like gradients of my loss, and I give you a bunch of Z, and I want to maximize this over V, and having like a constant factor guarantee, I think is not possible. Okay, so this will immediately allow me to learn correctly, because you can do Frank rules with approximations if those approximations are multiplicative. So this, I believe, this is not possible. But the only thing that I need, and this is where the problem gets interesting, is that this, if I want to preserve, so if I need this to be able to learn to minimize my empirical risk. Okay, but what I care about is not minimizing well my empirical risk. What I care about is doing well on unseen data. So this means, and we can take it offline because I will not have time to describe the exact reasons. This means that this only needs to be true for G being Gaussian. Okay, or Rademacher, anything which is random with zero expectation. So this means that now what I need is that I want to be able to maximize, to have an algorithm that can find an approximation of that maximizer, which only satisfies this for G being a Gaussian vector. Okay, what you can show is that that part, okay, it's a Rademacher complexity is 1/√n. So what you need is to be able to find an approximation V hat that for which, if you give it any set of Zi's and any like random vector Gi, it's bigger than 1/√n. Okay, and first a small bad news. So if you replace plus here by power 0, so just like the sign or just like the indicator function or the Heaviside function, is not possible, and it's still an open problem to see if this is possible in for that case as well. Yeah, so this is where I stopped, and if you have any idea on how to make this work, I would be very interested. I've also tried to replace, so the set, so here, this is a set of, this is a Lipschitz continuous, okay? And so what I was able to get that if you replace this by any Lipschitz continuous function, this is essentially almost equivalent to optimal transport. And for that you get an exponential behavior and not 1 over root n. All right, so now to conclude, so I presented like this classical convexification of neural networks. The idea is to go with infinitely many neurons, or in fact this can be this is true for any number of basis functions. The key here, and this was the goal of the work, was to show that with a single algorithm you can adapt to all structures, okay, linear functions, dependence on a subset of variables, and so on. Key as well is that the kernel methods are not adaptive in the sense that they need to consider all derivatives, and there is no adaptivity, whereas there is adaptivity if you start to learn the weights. You can do high-dimensional variable selection, so this is the positive side, and again on the negative side it's convex, but this does not mean you have a polynomial time algorithm. And what I've been able to do so far is to reduce this to approximate Hausdorff computation between the zonotops. And clearly this is one way of approaching the problem, okay? So there was a nice talk by Johan yesterday. There may be like other ways to attack the problem. So here I'm transforming the non-convex problem into the non-convex problem of adding a new neuron, okay? So we could go back to this empirical risk and show that what Johan is trying to show is also helpful. In terms of extensions, so clearly a lot, going to more than one layer. There was a very nice talk by Gita yesterday. Is it possible to extend some of it to multiple layers? Of course, multiple outputs, and clearly also to other models. Okay, so clearly, nobody really cares about like a single layer neural network, okay, because this is really doing something very simple. But if you start to add some more structure, and there's a nice paper by Zheng, Liang and Wainwright looking at the convolutional case, and so here I think they look at that case for the purpose of optimization. I'm not sure they have looked at the goal of adaptivity, okay? Because to me, if those neural networks will work well in practice for images, it is because they adapt to some structure on your data, okay, which is present in images. And we'll be interested to see if this is the case for the convolutional neural networks. And finally, there's also yet a third way to do optimization for the neural networks. I presented two: convexification by adding a neuron incrementally, trying to minimize the loss, or there are other ways, and there's very nice work by the team of Animan and Kumar, mostly based on tensor factorization. So here you assume that the model is correct. You construct moments and like third or fourth order moments, so that you can, which are big, so that if you factorize them, you recover your input weights. And this is totally different approach, more like moment matching instead of optimization, but this, I believe, could be combined as well. Thank you for your attention.
One question here.
Did you think about, or maybe it's too naive, but this idea that if you take like SGD, like basically design, and so what I understood is that you want to make it like non-parametric so that you can keep building the thing. Like if you do like a very naive thing where you do, I start with like n neurons, I do SGD for a number of steps, and then once I see that I observe some pattern of the algorithm, I keep on adding neurons. Is this analysis? Where does it break?
It breaks. It will break. It will break there. So how do you add a new neuron?
Okay. You start basically. You could say I add like random neurons, and then I just do SGD.
So if you add like an exponential number of random neurons, yes. But if you add a finite number, I don't know of any way of making sure you cover the potential like good neurons. Okay. So essentially. If you could show that you have sufficiently many neurons to cover all the attraction basins of the good neurons, that would work. But this is unlikely in practice. So this is something. I don't know if this is the correct approach, okay? So trying to compare neural networks which are over-parameterized to go to the infinite limit, okay? This is a nice way because it makes things convex. But whether this is really what you see in practice, it's hard because it's not, in fact, when you take that, when you take, what I say is a bit misleading, okay? Yeah, yeah. So this is like, you start from a finite number of neurons, and when k goes to infinity, okay, we replace the sum of Diracs by any measure, okay? There's a big jump between like Diracs and a full measure, okay? So it's a very big step. In the L2 case, that step is, there's nothing hidden, okay? So you replace the law of large numbers, it's fine, you always approximate a finite average by the expectation. But when you start to optimize, you are replacing a set of Diracs by any measure, and there's a big gap, and I'm not sure this is a good way to approach it, okay? Because at the end, you replace, so you remain convex, this is nice, but you go to this like barrier of incremental addition of a neuron, which I don't know how to do.
Is there any numerical evidence to show that your approximations produce a good or better result for real applications?
Good question. Okay, so in a sense, if you take like all applications of neural networks, okay, so if they work, it means that my theorem is correct. No, I'm joking. No, but I think, so here, okay, so let me answer correctly your question. So I've tried to, and many people have tried to, essentially here, if you believe the convexity of the approach, you have to use the incremental learning of neural networks. Okay, so people have compared minimizing the empirical risk directly with a finite number of neurons with adding neurons one after the other, and I think it works pretty much the same. I think there's no big difference. So if the question is, can I observe this? Can I observe this in practice, like my table? Those are very pessimistic upper bounds. Okay, so here, like all bounds in machine learning, there is a big O, and the O is really big. Okay, in the sense that the difference between like the exact performance and the bound is typically very large. So, I think that those neurons are really, those like neural networks are really adaptive to the, and much more than this. Okay, I think it goes much quicker. But if you make no extra assumptions, I don't know how you can do better in terms of bounds.